We're now going to look at a result that states that differentiability implies continuity. So we want to look at a theorem which states that if f of x is differentiable at a point x equaling c, meaning f prime of c exists, then f of x is continuous at x equaling c. Now this makes sense because if a function is differentiable at x equaling c, then near the point c f of c, it behaves very much like a straight line. And a straight line is continuous, right? Another way to say it is that if a function is differentiable, then it has a certain degree of smoothness to it. So if it's smooth, then it certainly has to be continuous. Now, an equivalent way of stating this theorem is to say if a function is not continuous at x equaling c, then f of x is not differentiable at x equaling c. Well, that makes sense because the original theorem says if a function is differentiable, then it must be continuous. So if it's not continuous, well then it couldn't have been differentiable. And that's what this alternate statement says. So let's look at an example, and then we'll prove this theorem eventually. So we have a function f of x. It is a piecewise defined function. It's x squared for x less than or equal to 1, x minus 1 for x greater than 1. And we want to determine if this function is differentiable at x equaling 1. Well, if we look at the graph of the function down here, if we look at the graph, we see that the function has a break discontinuity at that point at x equaling 1. So by our result right up here, we see that this function cannot be differentiable at x equaling 1. So f prime of 1 does not exist because of this break discontinuity. And just to verify that your function really does have a discontinuity there, notice if you looked at the left and right hand limits, and the limit from the left, and so you see your left and right hand limits do not equal each other, so the full limit cannot exist. So therefore your function is not continuous at x equaling 1. And if it's not continuous, it cannot be differentiable by this statement up here. Now let's look at a proof of this result. Now, before we actually get into the details of the proof, we have to create or look at an alternate form of the derivative of a function at c. So let's recall f prime of c we defined as the limit as delta x approaches 0, f of c plus delta x minus f of c over delta x. So that was the way we wrote the derivative at c. Now we just need a slightly alternate form of this limit definition. Well, let's notice that if we're going to do a little change of variables here, if we let x minus c be delta x, so we're going to replace this part right here is going to become x minus c. Then if I take c over to the other side, x is going to be c plus delta x. And so this part right up here, the c plus delta x, we're going to replace that with an x. And also note that as delta x goes to 0, that's equivalent to saying x minus c goes to 0, or x is approaching c. All right? So this part right here, the x plus delta, or the limit, delta x approaching 0 gets replaced with x approaches c. And so instead of writing our f prime of c in this form here, we can write it like this. Limit as x approaches c, f of x minus f of c over x minus c. This is just an alternate way of writing the derivative at x equaling c. And graphically down here, it's exactly the same as this definition right here. Because if you notice the f of x minus f of c over x minus c, if we look at our graph down here, you see we have, right there is c on the x-axis. Here is x on the x-axis, right here, here. And we form a little triangle and a secant line, like we normally do to define our derivative. And now notice that the rise is going to be f of x minus c. The run is going to be, that is x minus c right there. So the slope of this tangent line, sorry, the slope of the secant line, that's a secant line, so the slope of that secant line is f of x minus f of c over x minus c. And as we let x approach c, well, notice that this line is becoming the tangent line. See that? And so the limit as x approaches c of this quantity is approaching the slope of our tangent line. So this is just an alternate way of obtaining the slope of our tangent line right up here. This is just an alternate way of obtaining the slope of our tangent line. All right, now let's continue with the proof. So in the theorem, we are given that f prime of c equals the limit as x approaches c, f of x minus f of c over x minus c. This is our derivative, exists. And we want to show that so we want to show limit as x approaches c of f of x equals f of c exists. Now remember, this is just our statement of continuity of f of x at f of c. I'm sorry, at x equaling c. Remember, for continuity we have those three conditions, but we said that we could combine all three of those requirements into one statement. And so we combine them like this into one statement. So this is a statement of continuity of f of x at x equaling c, this requirement. All right, now let's notice that this is equivalent to stating that all right, so it's equivalent to this because all we did is move the f of c over to the other side, so the right-hand side becomes 0. And then we get the limit as x approaches c of f of x minus f of c equaling 0. So this is what we need to show. Showing this will be the same as proving this. Now let's first of all note that f of c does in fact exist, since in our definition of the derivative up here, we have f of c right here. So if f of c did not exist, then this limit certainly could not exist. So f prime could not exist. So f prime of c existing means this must exist. This number right here, it must be a number. This must exist. So that's since and now let's take a look at this. Let's just verify that this is true. So if we look at now we're going to do a little math trick here. So you see what we did is we multiplied by x minus c and just divided it back out. So we haven't changed anything. So we just did that math trick, multiply in, divide back out by the same thing. And also notice that the x minus c is never equal to 0 because x is approaching c but never actually touching it or reaching c. So this is never 0. So we're technically never dividing by 0. So there's no problem doing this. Now, if you look at this quantity here, what we have is this piece right here is approaching f prime of c, which exists. And this part right here is approaching 0 as x approaches c. And so this limit is going to be f prime of c, which exists, it's a number, times 0. And so this limit is 0. And we have proven what we need to. And so therefore, we now have that the limit and so therefore f of x is continuous at x equaling c. And that concludes our proof. All right. So that concludes this lesson on differentiability implies continuity.